Hello, my name is Samuel Cheng, and this is my Lab 5 Magnetic Braking with Faraday. In Lab 5, we are given the following scenario and task. Using an aluminum tube and a magnet, time how long it takes for the magnet to reach the other end. Then create a computational model of the aluminum-magnet interaction. In terms of a physical lab, this is it in its entirety. These are the main objectives of the lab. Collect observational data of a magnet falling through a conductive tube of aluminum. Create a computational model of the magnet-aluminum interaction. Compare the collected result to the computational result, and relate data and observation to the overall idea of Faraday's law. Although simple, this lab requires a deep understanding of the following key concepts and principles, which will be addressed and used throughout the entire lab. First, Faraday's law, which states that a changing magnetic field produces a Curly electric field at a closed surface. Quantitatively speaking, it states that the closed integral of the scalar product of the electric field and the small displacements around the closed surface is equal to the rate of change of the magnetic flux. This statement also gives rise to the fact that with a conductive loop around the closed surface, the magnetic field consequently produces a current, which will be useful in calculating the force by the loops on the falling magnet. Second, the Biot-Savart law relates the idea that a current produces a magnetic field, which will also help collect the force on the ring by the falling magnet. In addition, Lenz's law, which states that the direction of the magnetic field of an induced current is opposite in direction of the change in magnetic field of its source, and in this case, the falling bar magnet. Newton's third and second law will be useful for relating the gravitational force on the magnet with the magnetic force, allowing us to calculate the force on the magnet by the loops. These are the measured and observed data that I collect in this lab, as well as the final computational results of how long it takes for the magnet to fall through the tube. So the length of the tube was about 0.25 meters, mass was 0.023 kilograms, the width of the aluminum was about 0.011 meters, the inner tube radius was about 0.235 meters, the magnetic dipole moment was about 5.795 amp meters per squared. Average time is 3.53 seconds, and calculated time was about 3.256 seconds. This portion of the code describes the magnetic dipole moment of the bar magnet. This function was taken from previous results from Lab 3. As described earlier, the change in flux can be written in terms of the magnetic field, which in turn also describes the EMF. This is used later to calculate the current that runs through the loops. It's important to note that in this code, instead of calculating the force that one loop exerts on the magnet, it treats the tube as multiple loops stacked on top of each other. After calculating the EMF using the change in flux equation, the next portion of the code calculates the gravitational force on the magnet, which will be used to help calculate the net force on the magnet system. The last line in this portion calculates the currents in the loop. In the first line, line 175, is where the function for the magnetic dipole moment is used to calculate the magnet's dipole moment. The next line is where the magnitude of the force on the bar magnet is calculated, which is equal to the current, which was calculated earlier, multiplied by the circumference of the loop, the magnetic dipole moment of the bar, and sine theta, because only the y component of the force is necessary. Using Newton's third law to describe the net force on the system, we could describe its velocity and position using Newton's second law. This is the result of the lab when the code was run. The picture on the right was caught picture on the left was caught mid-fall, but the graph is the case when the magnet falls all the way down. So the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. So which color corresponds to clockwise current and which counterclockwise? So we know that red is the counterclockwise direction because using the right-hand rule, we determine the direction of the current with Lenz's law. The blue is clockwise. What happens to the dynamics of the system when you flip the magnet around? So regardless of the orientation, the time does not change. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? Well, the computational model was definitely faster than the real-world observation. This was probably due to the fact that the magnet would rattle downwards along the tube. The computational model could be made more accurate if we modeled the tube with more loops. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? In the velocity versus time graph, where the slope is 0, it can be concluded that the force in the system is in equilibrium, because without slope, that means that the system is not accelerating. and because the magnet is not accelerating, the system is in equilibrium, and that all forces on the bar magnet sum up to 0. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, if the resistivity is close to 0, then the current would begin to approach infinity. In this case, the magnet would fall a little and then be shot up straight away. What if there were holes or slots in the tube? How would this affect the ring currents in your model? If there were slots or holes around the tube, the force acting on the magnet due to the current would no longer be just in the y-axis. That is all for that pipe. I'm currently on the train back, so I apologize for any outside noises or distracting sounds. Thank you.